Hello, and welcome to another physics lab entitled Extreme Rope Swing. In this lab, we will be modeling the motion of a person as they swing on a very large rope swing, which can be viewed by clicking on the link in the description. Of course, in this lab, we will be using VPython to quantitatively model this motion, and as a result, we will look at determining the locations where the tension and stretch are the greatest, as well as their values. We will also look at the velocities at certain points in the motion, as well as the energy of the system, which includes the rope, person, and the earth. Now let's take a look at the physics principles. The two big principles we will be using today are Newton's second law, or the momentum principle, as well as the energy principle. The formulas on the screen are ones explaining the principle. However, there will be derivations of these two principles in the upcoming code in order to get values such as velocity or position at a certain point. Now that we have the fundamental principles down, it's time to move on to the code. Here we have some initializations where the mass of the person is 75 kilograms, which I assume was about average for a male, such as the one in the video. Next we have the place where the human jumps, assuming that he is about eye length with the top of the arc on which he jumped from and a rope's length away. We also say that the jumper starts at rest. For the other initializations, we have gravity, a spring constant, a stretch length, and formulas for calculating initial energies. Let's look to see how we calculated the spring constant. Using a formula for period, we can find the spring constant. The period was around 7.5 seconds in the video, so that is what is used. L0 is set to a number where the stretch in the rope begins slightly after the jumper falls. Now we can move on to the while loop. Here we define the initial energies of the system, the forces acting on the jumper, and the derivations of Newton's second law in order to find velocities in position. The if statement is there to get rid of the spring-like force if there is a negative stretch. Since this is a rope we are dealing with, we expect the rope to exert a force on the jumper if and only if there is a positive stretch. The next part of the iteration determines a stretch length for each time step as well as a new energy. The if statement takes into account that if there is no force on the rope, the rope potential energy is 0. Now we'll look at the motion of the jumper when we run the code. As you can see, the path it stays on is pretty consistent because we have not included any external forces such as drag that would slow down the jumper. And in the model, the blue arrow determines or displays the force of the rope, and the black arrow displays the gravity force. Looking at the energy graph, we can see that the total energy, which is displayed in yellow, is 0 all throughout the motion. Because we included the rope, jumper, and earth in our system, this is what should be expected. Using the same code, we can print out values for what we want to calculate in order to quantitatively describe what is going on during this motion. First, let's look at tension, or we'll look at where tension is the highest in the system. By printing out the magnitudes of the tension force, we are able to see where in the curving motion the tension force is the greatest. Here we can see that around here, where the tension, or where it's in the bottom of the swing, the tension is greatest. We expect that here because dp/dt parallel is 0, and dp/dt perpendicular, or the tension force, is the only thing acting as a net force. So we should expect that to be where the tension force is the largest. Next, we look at where it underwent the largest stretch. By going through the same procedures, we can see where S is the greatest. Once again, this value right here is where S is the greatest, where it is also on the bottom of the swing. Finally, we will examine what the velocities are at certain points in the motion. By printing out values for velocities near the position in the picture, which are the ones circled, we can get a good approximation for what the velocities and magnitudes of the velocities are at each point. So the first one, we have an average velocity of 9.59, a negative 18.37, and a magnitude of 20.72. In the second part, we have average velocity 1.62 in the x direction, 14.81 in the y, and average magnitude of 14.89. Then we have average velocity from these values about 15.58 in the x direction and 2.66 in the y direction, and average magnitude about 5.81. And you notice here that because in the second picture where the x velocity is quite small compared to the y velocity, and in the right picture where the y velocity is quite small compared to the x, that in this case the y value contributes mostly to that magnitude, and the x value contributes mostly to the magnitude in the third problem. So in conclusion, using fundamental principles such as the momentum principle and energy principle, quantitative descriptions of a person's motion on a rope swing can be made. And these principles also can explain why these values are such.